Here's another way to think about length contraction. We'll start, as we often do, by thinking about space and not space-time. So the spatial world that we live in is three-dimensional. There's this motion, and that motion. So three directions or three dimensions. And there are objects in that world, objects like Beowulf, objects like the stick, physical things that have a physical reality independent of observers and coordinate systems and so on. We could ask, though, about the shadows that a three-dimensional object might cast. So here is a shadow of the stick, and the shadow has a certain length. But as I move the stick, the length of the shadow changes. Similarly, here is a shadow version of Beowulf, and as I move Beowulf around, his length and his height change. But Beowulf doesn't change. He's Beowulf. He's the same size, the same physical reality, but the two-dimensional projection of him on the blackboard in my office changes. So the way I was doing this is I was moving Beowulf around. And as I move Beowulf around, we get different projections, different shadows. But we could also do a similar thing if I held Beowulf at rest, and instead it was the blackboard that was shifting around. So maybe the blackboard is part of a coordinate system, and somebody's rotating that coordinate system in three-dimensional space. And in so doing, they'll observe different lengths on their two-dimensional surface, depending upon the angle of their reference frame. So now let's think about space-time and not just space. So space-time is four-dimensional, the three dimensions of space plus time. So 3 plus 1 is 4 dimensions. So suppose we want to think about now. What is now for a particular observer? Well, that would be the collection of all the events in space-time that occur at a particular time, the time that that observer would call now. And so then we've taken time out of the equation, out of the picture, and we'd have a three-dimensional space and not a four-dimensional. So now is like the shadow of a four-dimensional figure in three dimensions. So when you make a shadow, you lose a dimension, right? So Beowulf is three-dimensional, and we look at his shadow, and his shadow is a two-dimensional image on the blackboard. Now is a shadow of four dimensions, sort of projected onto not a blackboard, but three dimensions of space. So just as Beowulf looks different depending on the angle of Beowulf, or if I could move it, the angle of the blackboard itself, so we're going to have different ideas of now for observers in different reference frames. Because remember, we don't all agree on what's simultaneous. We don't all agree on what now even means. Different observers have measured different things as simultaneous. So to think about length contraction, there are objects, real physical objects whose reality doesn't change, but how they get projected onto space and time axes depends on the reference frame, depends on the angle of the blackboard, depends on the speed of the reference frame. So, again, length, what one observer might call length, is a particular shadow. What another observer might call length would be a different, would be just a different shadow. We could talk about maybe the rest length, or like the true length would be a shadow, maybe where I had the length that was perpendicular to the light, and then anything else would be smaller. Similarly, the rest length, that would be the shadow, so to speak, onto the x-axis in a reference frame where that object was at rest. So I hope this shadow example has been useful and not too spooky with this flashlight shining in my eyes and on my face. But again, the main point or the take-home message is that what we call an x and a t measurement, you can think of as a shadow projecting a higher dimensional structure down onto a lower dimensional structure. And we know that shadows can look different depending upon how we orient the object or how we orient the surface or three-dimensional space onto which that object is being projected.